So what is free energy? What's the difference between free energy and everything else we've been doing? Free energy is the maximum amount of energy released from a system that can do work on the surroundings. Think about it. Any reaction you have, right? If we have some exothermic reaction, we know that heat is going to be released. Okay. But some of this heat is released into the surroundings to increase the entropy. So that means that heat isn't available to do any work. So the only heat that's available to do work is the free energy that there actually is in the system. So here's a reaction, right? Carbon going to methane. Okay, carbon and hydrogen going to methane. What's happening is the delta H value, this is the enthalpy, is negative 74.6 kilojoules, meaning that it's exothermic, it's giving off heat. Okay, so if it's giving off heat, can all of that heat be used to do work? No, unfortunately. You would have to calculate delta G. So delta G tells us that only 50.5 kilojoules of that work, of that heat, can actually be used for work. It is our free energy. It's the energy that we do not lose to our surroundings. So even though we had 74.6 kilojoules of heat that was lost, right? 24.1 kilojoules of it was just lost to the surroundings. Only 50.5 kilojoules of it actually did work. And so that is what our free energy is. It is the energy that we actually have left to do work, thus making this reaction spontaneous. If we had a reversible reaction, then the free energy is the theoretical limit of work that can be done. So what that means is, even though back here we said that the maximum amount of work that this reaction can do is 50.5 kilojoules, most likely that is not how much work will be done. Most likely it will be much less than that, because some of this work will also be left as heat, other entropy sources make things speed up. There is all of this extra energy that is lost to the surrounding. So the maximum amount of work that we can do is 50.5, but most likely it will not be 50.5 kilojoules. The only time that it actually does end up equaling the free energy is when we have a reversible reaction. The reason is because reversible reactions happen so incredibly slow that it would be like taking one grain of sand away. So if you take one tiny, tiny grain of sand away, right, we can easily measure or relate the energy to how much has been lost. And so that is the only time we would reach our theoretical limit, is when we have a reversible reaction. If we don't have a reversible reaction, then we will end up just having heat that is being lost. Think about your motor, right? You have a battery, there is some current going to the motor, but we know if you touch the top of that hood, you end up having heat that's being lost. So there was only so much current, so much work that could be done from that battery to the motor, because some energy is lost as heat. So that would be our Gibbs free energy, is how much energy we actually can put into our system. Oh, and here is the picture, right? Some energy is lost to our surroundings. Therefore, a real reaction would not be reversible. If we're under non-standard conditions, so our delta G naught, right, is equal to delta G when we are under standard conditions. So they're at their normal state temperature, right? They're at 1 atm of pressure, 1 molar concentration. If we're not under standard conditions, we do have an equation that relates delta G naught plus RT ln of Q, because Q is when we're not at equilibrium, right, to our delta G. Q is our reaction quotient. If we are at equilibrium, our delta G value equals 0. So therefore, we could just solve delta G naught is negative RT ln of K, right? K because we're at equilibrium. Our temperature does need to be in Kelvin, and then we're using the R of 8.314 joules per mole Kelvin. Because remember, our units of Gibbs free energy are in joules, so that's why we would choose that gas constant. So here's a reaction. They give us a delta G naught value, and they ask us to solve delta G of our reaction when it's under these conditions. Is this reaction more or less spontaneous than under standard conditions? Well, let's see. We have an equation, right, back here that we could compare. So they gave us delta G naught. They most likely gave us a temperature. I didn't see it right off, right? But we probably have some temperature. R is a constant. Q is our reaction quotient, products over reactants. So let's take a look. They gave us the pressures, right, of our products and our reactants, so we could solve our Q value. They did give us a temperature, 298 Kelvin, right? So we can go ahead and plug that in our reaction. So our Q is the pressure of NO2 squared, right, because we got two of them, divided by the pressure of NO squared, because we got two, and then oxygen, just one of them. So if you plug in those pressures, you should get Q is 4 times 10 to the third. You can then go ahead and plug that in your reaction, your expression. So delta G equals, well, it wants delta G naught of our reaction, which is negative 71.2 kilojoules. Remember down here, our R value is in joules per mole Kelvin. So let's go ahead and convert that to joules. So then we're adding R, which is our gas constant, multiply it by T, 298 Kelvin, ln of Q. So ln of our Q value. If you go ahead and solve that out, you end up getting negative 50.7 kilojoules. So that is our delta G when we are at 298. Well, let's see. We compare this delta G value, negative 50.7, to negative 71.2. Which one's more spontaneous? Delta G is spontaneous when it's negative. The more negative one will be more spontaneous. So it looks like this reaction is more spontaneous under standard conditions than it is under these new conditions, under these new pressures, because we got a less negative number. So it is less spontaneous. Go ahead and try this one. Pause the video, try this, and then check your answer. So when delta G of our reaction equals 0, we are at equilibrium. So we can just say delta G naught is equal to negative RT ln of K. The reason for this is because when our K is less than 1, our delta G naught is going to be positive, and our reaction is going to be spontaneous in the reverse direction under standard conditions. So if we don't have any products yet, right, nothing will happen. But our delta G, our K is less than 1 because if we look over here, so here we have a K value less than 1. If you think about it, K less than 1 means that our reaction needs to end up going to the left, right? Our Q to equal our Q equals 1. So our reverse reaction will end up being spontaneous. Whereas if we have a large K value, it wants to be spontaneous in the forward direction. If we are at equilibrium, right, our Q would equal 1, our K would equal 1, and then we wouldn't need to worry, right? We'd be at equilibrium. Our change in our G value would be 0. So based on which direction we're going, our K value will tell us about our Gibbs free energy. So it wants us to calculate the free energy of formation, or use the free energies of formation to calculate the equilibrium constant. So how would we calculate the equilibrium constant? Do we have an expression? Well, we could use our delta G naught reaction, right, is equal to the sum of our reactants minus our products, because that's what they gave us. They gave us delta G's of formation. So if we solve our delta G of formation, this is our products, right, minus our reactant, so 2 times NO2 minus N2O4. We go ahead and solve that out. We get delta G naught of our reaction is 2.8 kilojoules. It wants, though, the equilibrium constant. Equilibrium constant is K. We have not solved for K, right? Make sure we're answering the question. So we do have an expression that tells us delta G naught is negative RT ln of K. We can go ahead and rearrange this equation to solve for K, right? So the ln of K is negative delta G naught reaction over RT. Plug in delta G. So once again, make sure you change that to joules per mole divided by R and T. So we got the ln of K is equal to negative 1.13. If you look on your calculator, the opposite of ln is E. So K would be E to the negative 1.13. So our K value would be 0.32. So that is our equilibrium constant. That is then the end of the chapter. So please make sure you do the homework, do the discussion posts, and I will see you in our next chapter.